So welcome students. So in this series of lectures that we have been planning for IOQM geometry, we have gone through straight lines, angles, triangles, quadrilaterals, circles. So we had just initiated circles in the last lecture. In this lecture we will deal with some properties of tangents to circles. Even though in the previous class we did discuss things about tangents also, but here today we will try as much as possible to deal primarily with tangents, and if the time allows we will move forward with say Ptolemy's theorem and stuff like that. So tangents, as we know, the things that we covered in the last lecture were the very elementary notions. Say this is center, that radius and the point of tangency is perpendicular to the tangent. This is what we covered, followed by angle in the alternate segment are covered. This is basically just a recap of our last lecture. These are the things that we covered in the previous lecture. These two things we went through. Also, we saw that tangent from an external point are equal in length. We also went through this theorem, we proved it if you remember. PA into PB is PT square. This is also something that we covered in the last lecture. And at the fag end, what did we cover? Since these angles are 90-degree, circle with CPS diameter will pass through these points of tangencies. So I just took your first 5 minutes to make you recall the things that we covered in the previous video. Now we also did questions on it. Now further we are going to see uh, common tangents to two circles. Tangent something is something that we covered. Now insofar as common tangents to two circles are concerned, this is the new thing that we are going to take up today. I just made you recall all this because as we proceed in this lecture, we will be requiring to use this. Okay, this is something very trivial, you would have gone through in say class 8th or 9th. This is a theorem that you would have angles in alternate segment are equal. This is something that you would have seen in say your NCERT text of 10th. This I think is something which can very easily be calculated because these two triangles are congruent. PA into PB is equal to PT square is something that we did using similar triangles, if you recall. Okay, so these stuff is something that has been constantly asked, and you should try to correlate problems given with the situations that we are dealing with. Now insofar as common tangent is concerned, if you take two circles, say one lying outside the other completely, okay, These are common tangents to these two circles. AB and so this is PQ. Okay, so AB is direct common tangent. PQ is transverse common tangent. Okay. Now, this is also called external common tangent. And this is called internal common tangent. Now, say if this is the center, so C1, C2, this is say T1, T1 and T2. What we see is that in circles, sorry, line joining the centers C1, C2. So, what we see is that internal common tangent divides the line joining the centers in the ratio of radii. External common tangent two divides the line joining the centers externally in the ratio of the radii. Okay. This is something that should be kept in mind. It is a very vital thing. We will further move with finding the length AB and PQ, but at the very first go we should be able to remember this. What is this? That the line joining the centers. Okay. So, the internal common tangents divides the line joining the centers in the ratio of radii internally. External common tangent divide the line joining the center externally in the ratio of radii. Okay. I think we will be able to prove it. How do we prove it? Say first and foremost, let us prove that they meet on the line joining the centers. So, what we say is that suppose we draw this line, say C1, C2, this is T2, this we marked as AB. Okay. So, what we are saying is that suppose AB meets line joining centers at T2. This is R1 and this is R1, sorry, this is R2. Now, we can very easily see that these two triangles are similar. Which two triangles? T2A C1, T2B C2. Okay. So, what is the ratio of C1 T2 upon C2 T2? This is R1 by R2. Okay. Now, let the other tangent, common direct tangent meet it at, say, for the sake of simplicity I am taking it T2, otherwise ideally we should take it to be some other point, and then we can again say, suppose this is T2 dash, then we can say C1 T2 dash upon C2 T2 dash 2 is R1 upon R2, meaning thereby that T2 and T2 dash coincide. I think we can very easily see that this is the same thing that we are going to do for internal common tangent. So, this establishes the fact that direct common tangent meet on the line joining the centers, and so would, I think you can now understand how we will do for this one. We will draw this diagram, and similarly we will draw this diagram, and then we will say T1 and T1 dash, they divide in the same ratio R1 is to R2, so they must be coinciding. So, this is the first thing. That okay, direct common tangent divide the line joining the centers in the ratio of radii externally, and so would be internal common tangent divide agreed. Okay. Now, if you want to find length AB, what do we do? Suppose we have to find length AB. Okay. C1, C2, A. So, what we do is that from point B, we draw a line parallel to C1, C2. Okay. So, if this is R2, this 2 is going to be R. So, what is the remaining length? R1 minus R2. This you can very easily see the parallelogram. This is C1, C2. This angle is 90 degree. So, we can find AB as this is the length of direct common tangent by simply Pythagoras theorem. Okay. Now, for transverse common tangent, what will be the length? Diagram is bit rough, so Please pardon me. So this is R1. This is, sorry, R2. Now what we do is that let us extend it. Okay, fine. Say this is R2, we extend it, say like this, and then we draw a line parallel to the tangent, so parallel to PQ. So since it is parallel to PQ, this angle is going to be 90 degree. Okay. So you can see that, see, we have drawn a line, this, see, these two are parallel, fine. Since this angle is 90, this angle is also 90. Further, if you are able to see, since these two are parallel, they are always parallel. Okay. So what you will have, if this is R1, so this becomes as such a parallelogram. In fact, not even a parallelogram, this becomes in fact a rectangle. So if this is R1, this too is going to be R1. So I think we can find now further PQ will be equal to say C1 T. PQ will be equal to C1T in this rectangle. Now PQ and C1T are equal. What is C1T? By Pythagoras. So this is length of transverse common tangent. Fine. So length, see, if you are able to recall the expression in the previous one, in direct common tangent, this was simply R1 minus R2 whole square. So insofar as remembering the expressions are concerned, C1, C2 is what distance between the two centers, and for direct common tangent, it is of say its length is more than transverse common tangent, just we can have a perception like that. This will be R1 minus R2 whole square, and for transverse common tangent it is R1 plus R2 whole square. So these two things we must keep in mind. Okay. So a very simple question that is asked is that suppose somebody say, if square of length of direct common tangent is 100 and square of length of transverse common tangent is say 36, find product of radii. So what we just found out, the expression is 36 C1 C2 whole square is 100. If but that's it, just subtract it. Okay, so 4R1 R2 is 64. So R1 R2 is 60. Fine. Now, again, this is a very trivial problem, generally not expected in exams. You are generally given diagrams to deal with it, okay. So, if you are given length of the two common tangents, then we can find what are the, then from that data we can get what is the product of radii of the two circles, okay. Now, moving ahead, what we can see is that if distance between center is r1 plus r2, so length of transverse common tangent becomes 0. So, what are the various possibilities? When is the distance between centers r1 plus r2? That is when the two circles touch each other externally. So, what are the possibilities? How can two circles be placed? See, you can see two circles can be like this, as we had earlier drawn. So, here what happened was that they were not meeting each other at any point, not even. So, you have 4 common tangents. Now, when these two circles move towards each other and this is the situation, what do we have? These two, see, if you see these two tangents, they, as the two circles move towards each other, these two tangents, they keep on, they are getting rotated and finally they coincide to become one tangent. So, when C1, C2 is R1 plus R2, we have 3 common tangents. Okay, we have 3 common tangents. Please remember this. In this case, we are, if you see, what is the length AB? So, here you are going to put R1 plus R2. So, R1 plus R2 whole square minus R1 minus R2 whole square. What do we get? Here you see AB, the length of direct common tangent is 2 root R1 R2. Okay. This becomes, of course, these two points are one is the same, the point of contact remains same. So, transverse common tangent, the length effectively is 0. Now, moving ahead, if these two circles intersect each other, okay, if these two circles intersect each other at 2 distinct points, then you only have direct common tangents. So, when C1, C2, distance between centers is less than R1 plus R2 and greater than R1 minus R2, we have 2 common tangents. Now, if the circles touch each other like this, one lying inside the other, okay, one lying inside the other, that is when C1, C2 So we only have one common tangent. Okay. Now, what is the other situation that is remaining is that if one lies inside, completely inside the other. In this case, C1, C2 is, so we have no common tangent. Okay. So these are the possible situations insofar as common tangents to circles are concerned. That is, if the circles do not meet each other at any point and one lies completely outside the other, we have four common tangents. Okay. If they touch each other, this is what we say is they touch each other externally. Okay. If they touch each other externally, then we have three common tangents. If they intersect at two distinct points, so please remember this. This is the condition that the circles intersect at two distinct points. The distance between their center is less than sum of their radii and greater than the absolute difference between their radii. Okay. When they touch each other internally, distance between the center is the difference, absolute value of the difference between their radii. And one lies, and if one completely lies inside the other, then this is less than mod R1 minus R2. Okay. Now suppose somebody says a question like this. Okay. Let me say, let C1 and C2 be center of two circles. One with radii 10, radius 10, and other with radius r. Where r is a positive integer. If C1, C2 is 15, find the sum of all possible values of r for which these two circles have a point in common. Now see, have a point in common. I could have rephrased this, have at least one common point. See, these two would mean one and the same. So, what are the situations that we are looking for? What is the possible situations that we are looking for? Primarily, we want circles to be like this. Okay, this is C1, this is C2, this is given to you as 15, this is 10, this is R. Okay, they could also be touching each other externally or internally. A point in common. Have meet at two distinct points is not the language. Have a point in common does not mean that there is only one point in common. Okay, so please keep the language of the problem in mind. Have a common point. Okay, these two curves have a point in common. That does not mean that there is exactly one point in common. That means that there is at least one common point. So, what we are going to say is that C1, C2 is less than R1 plus R2 and greater than R1 minus 15 is less than 10 plus R and greater than 10 minus R. So, we can very easily say R is greater than 5, okay, from this inequality. What does the other inequality tells you? Oh, sorry. So, we can square it. Okay. So, R is this is for this situation. Now, do we want the circles to touch? Because we want they have a point in common. So, I think these two situations would also be acceptable to us, isn't it? So, ideally, because we want a point in common, we should put equality sign everywhere. That would suffice. So, R can be any number from 5 to 15. Okay, so sum insofar as sum is concerned, we have 11 numbers. This is 110. Or we could have simply drawn a diagram. See, if you see, this is one circle. If we are comfortable with geometry, I would say this would be a better way. So, this is 10. This is 5. With this as center, we need to draw circle. Okay. So, we have to draw circle of at least radius 5. So that we can draw a circle of larger radius, no issues. And what is the maximum possible that we can go for? With C2 as center, this is 15. Did I make some calculation error? This is 15, sorry. Oh, this is 15 square. This is Oh, so this would put together give you R is from 5 to 25. Very sorry. This would be 21 by 2 into 5 plus 2 and 15 into 21. That is 315. Very sorry. So the maximum radius that could be is 25. Okay. So algebraically, if you make an error, you don't get to know it, even though this is a very bad error. Such error should not be made. That 15, I wrote it as 5 only. Okay. That is why I was worried. How come we got 5 here? Anyways, so this is a question that is very easy, so to say, one of the easiest problems you can possibly conceive of. Now, further, suppose we ask you a question like this. Suppose somebody asks you a question like this. Given two circles which are touching each other. This circle passes through 3 commas, say. Let us not use coordinate geometry. Say A and B are two fixed points. A circle is drawn passing through A. Another circle is drawn passing through B. These two circles touch each other externally at point P. Okay. So, if AB is 10, find AP square plus BP square, given that AB is common tangent to the two circles. This is our question. Okay. So, what further data is provided? We are being provided with the data that AB is common tangent. So, what is the situation? That AB, okay, fine, touch each other. So, AP square plus BP square. Now, if it turns out, say, that this angle is 90 degree, then we are through. Again, this is not the solution to the problem. What I am saying is that if this turns out to be 90 degree, our issues are solved. Okay. So primarily what we are going to do is that we are trying to find the angle at this point. These two angles are of course 90 degree. Okay. Now if this is theta, this is 90 minus theta. Okay. This is theta, this will also be theta. If this is phi, this is 90 minus phi, and this is phi. What is this angle? 90 minus theta, 90 minus phi. So this is going to be theta plus phi. Now you can see 2 theta plus 2 phi is 180 degrees. So theta plus phi is 90 degrees. Okay, that means what is the situation? The situation is like this. Now I think this is known to us. So AP square plus VP square, you can very easily say is nothing but 100. So one thing that you can keep in mind or probably remember is that if the two circles touch each other externally, then their direct common tangent subtends a right angle at the point of contact of the two circles. Okay, at the point where the two circles touch each other. Again, we should be vigilant enough, we should have the wherewithals to write these 3-4 lines. You can see it is not a very typical ask that we are going for. Okay, this is something that we should be able to do it very easily. Further, we can say since this is 90 degree, circle with ABS diameter will pass through point P. So these are the things that we can expect. Now moving ahead, if you see, suppose you are given two circles, okay. I am not deliberately writing the languages of the problem, I am drawing the diagram itself, okay. Suppose you have two circles like this. And we have their direct common tangent. And so this is a smaller circle. Okay. Suppose this is R1 and this is R2. Say R1 is greater than R2 and this is small r. So we have to find R. So what is the language of the problem? The language of the problem is that two circles touch each other externally and they are also tangent to a line. A third smaller circle or say a third smaller circle is drawn touching the two circles externally and also their common tangent. What is its radius given that the two circles have radii R1 and R2. So I think Direct common tangent notion can be used. What is AC? What is the length AC? We just have seen that it is when the circles touch each other externally. The length of direct common tangent is 2 root R1 R2. So, what is AC? What is BC? And what is AB? So, AB is AC plus BC. So, you have okay. So, what is the situation? We divide it by say root R1 R2, root divided by root R, root R1, root R2. So, what you will have is that 1 upon root R is so what is R? I think you can very easily see is this is the radius. Now, I was given a smaller circle. Otherwise, what would have been the situation? Suppose you would not have been given a smaller circle. What are the possibilities that we could have seen? See, these are two given circles. Suppose the word smaller had not been used. Okay. R now, had this not been the case, we could have drawn a circle like this if you are able to fathom. Okay, something like this. Very large circle. Let me draw the diagram properly. These two circles have turned out to be too big. Suppose this is R1 and R2. So we would have drawn a circle like this. Okay. This two is satisfying both the conditions. So here what we would have had is 1 upon root R. So, subject to the given situation, had the problem not been specifically stated as find a smaller circle, we would have had two circles. We would have had two circles like this. Okay. Just wanted to know generally what happens is that you are given the diagram and we just write this, but we should be able to conceive the fact that there are two such possibilities. Okay. Now let me come up with one more problem. C1 and C2 are two circles of radius 10 and 6 respectively. Such that these two circles have three common tangents. Such that these two circles have three common tangents. Okay. Now, in circle of the triangle formed by common tangents C1 and C2 is drawn, and let R be the radius of this incircle. Find the value of R plus 6 upon 10 minus R. ठीक? So, this is our question. I have just framed the question. Now, what is the possible situation? When do two circles have three common tangents? When do they have three common tangents? We have just seen it is when they touch each other externally. So, if they touch each other externally, what is the situation that we have? This is the situation. In this case, we have two direct common tangents. And one transverse common tangent. Now, just look at this diagram. I think this completes the solution, isn't it? If you look at it, the smaller of these two circles plays the role as incircle of this triangle. These are the tangents. So, this is smaller circle is playing the role of incircle of this triangle. So, what can very easily be seen is that R is nothing but the smaller of these two, which is 6. 10 is radii of one of the x circle. So, this is a very simple question, 6 plus 6 upon 10 minus 6, that is 3, isn't it? Okay. So, just by drawing an appropriate figure, we got to the crux, or we actually got the solution. So, if you are trying to find the incircle, you should understand the tangents, the 3 tangents are touching the circles. Okay, the 3 tangents are touching the circle. So, these 2 circles will effectively be either the incircle or the x circle of the triangle that is formed by these tangents. The smaller one is the incircle and the larger one is one of the x circles opposite to say Q, isn't it? So, just looking at this, we can possibly fathom this rationale. Oh, क्या हो गया? अरे, sorry. Now, what more we can think of related to problems regarding this? Now, let me take you to a problem which has very often been asked in various examinations. Earlier, it has been asked in KVPI also. Question of similar nature. Okay, IOQM, JEE, or KVPI, NTSE. These problems based on simple notions could be asked. They have been, I think the problem that I am taking has been somewhat asked in these examinations in one way or the other. May not literally be the problem that I am discussing it, but in terms of the idea that the examiner wished to ask, it is the same. So, what we are given is, let me write the language so that you draw the diagram. Okay. For my own benefit, I generally draw the diagram so that that part at least can be excluded. But in examinations, that will not be the case. You will be given statements and you draw a diagram on your own. So, because we are in conversation, this is a lecture, we have been in conversation. So, just to save time, on some occasions or effectively on lot of occasions, I have taken the liberty to draw the diagram and then explain you the problem. Generally, it is the other way around, because we are in conversation with each other. We have taken certain liberties, but the examiner will be in conversation with you for the first time. So, you should be good enough to grasp the situation given in the problem, comprehend it and draw appropriate diagrams. Generally, I see diagrams are very rarely drawn. Okay, you have to draw it on your own. But drawing a good diagram in geometry is on most occasions effectively, in my opinion, half the solution. Okay, so just understand. Therefore, you should definitely practice previous year problems or problems from standard text and books, so that you get to know that how do you comprehend from the given language from the given data, an appropriate figure, a proper diagram, which will lead you to solving the problem. Now, insofar as this question is concerned, let me say that let C1, C2, C3 be circles such that circle Ci externally touches Ci minus 1 and Ci plus 1 for all I equal to also. R1, R2, R3 are radii of C1, C2, C3 respectively. Further, R1 is equal to 1, this is our problem. Find n given that there exists a line L tangent to all the circles let me write this also. It is given that it is given that centers of C1, C2, C3 are collinear. This is how generally questions are given. Okay, I may have not written it properly. As the question came to my mind, I have tried to provide you with the information, language but generally a very uh, typical language is used, mathematically precise language is used, so that nothing is left ambiguous. I could have simply drawn the diagram and told you that find this, okay. But now this is how generally you see the problems that occur in examination. So what is the question saying? Let C1, C2, C3, C4, Cn be circles such that circle Ci externally touches Ci minus 1 and Ci. So so C2 touches C1 and C3 externally, C3 touches C2 and C4 externally, okay. C4 touches C3 of course and C5 externally, and so on. Cn minus 1 touches Cn minus 2 and Cn externally. Also their radii C1. Further, you are given radii of two of these circles, you are given sum of the radii, and you have to find the number of circles. What other data is provided? That there is a line which is tangent to all the circles, and centers of these circles are collinear. So what is the possible situation that you are reckoning? So what is the possible situation that we are reckoning? Look at it. There is a line on which all centers of all the circles lie. These circles, the information which is provided at the last would be the initiating one, I think. Say first circle, hmm, first circle is of one radius. Then you have C2 which is touching this one externally. Okay. And what is given is that there is a line which is tangent to all of them. You can possibly easily understand that it cannot be the transverse common tangent. It has to be a direct common tangent, okay, something like this. In fact, if there is one line, you can say that there will be one more line. This line bisecting the angle. Okay. Now, and then we can keep on drawing. So this is the situation. So first and foremost, from the given data, are we able to draw the appropriate figure which would help you out? Now, what to do? Okay, you are given R1, 2, 3, 4. Let me draw one more. And we can keep on drawing. Now what to do? I think you can understand here, just as we saw while proving that external common tangent divide the line joining the centers externally in the ratio of radii. So we can deal with similar triangles, stuff like that, okay. Suppose I say this point is A, C1, C2, R1, R2, okay. Hmm. So, we can say AC1 upon AC2, AC1 upon AC2 is R1 upon R2, isn't it? Now, this angle AC1 upon AC2, okay. So, how can we proceed further? Now, this angle you can say, this angle is fixed, okay. This angle theta is fixed, isn't it? There exists a line L and C. So, angle between the tangent to all these circles and the line on which center of these circles lie, this angle is fixed. So, AC1 upon AC2 is R1 upon R2. Now, basically I am deliberately trying not to incorporate trigonometry, okay. Otherwise, we would have, since it is a right angle triangle, but I think sin theta cos theta is something that you might very easily be aware of. So, let me use that, okay. AC1, what is AC1? AC1 is R1 by sin theta. And what is AC2? It is AC1, that is R1 by sin theta plus R1 plus R2, because the circles are touching each other externally. Now, we can very easily see that this is also equal to R2 by sin theta. Theta is fixed. So, what does this give you? R1 into 1 plus sin theta is R2 into 1 minus sin theta. So, what is R2 by R1? And so will be R3 by R2, so will be R4 by R3. So, this, since theta is fixed, this ratio is fixed. That means the radii of this circle, the radius of these circles are in GP. This is a fixed ratio because theta is a fixed number. Okay, if that common ratio is R, you are given R5 is 16, it is R1, and let the common ratio be, say, capital R. R1 is given to you as 1. So, capital R is 2. Somebody may ask you theta also. What is theta? I think you can find 1 plus sin theta by 1 minus sin theta if it is 2. What is theta? But here the question is, if so, the common ratio turns out to be 2. Okay. Now, what you are given is that sum of all the radii is 4095. Okay. So, 1 plus 2 up to 2 raised to n minus 1 in fact. So, this is 2 raised to n minus 1 upon, this is given to you as 4095. So, 2 raised to n is 4096. So, this is 4096, 64 square, 2 raised 1024 into 4. So, number of circles is 12. Okay. So, this lecture completely covered questions regarding common tangents. Now, other things about circles we will read as we move on. Okay. Primarily today we covered things regarding common tangents. Again, as always, we try to prove everything, and if we haven't proved anything, it is our sincere request that please go through and prove it on your own. Okay. Further, just by looking at the lectures, you are not going to gain much. Again, take your time, give yourself time, solve as much problems as you can. Just by looking at the notions, it will be very difficult to fathom it, and ultimately being able to solve problems that finally appear in the examination within that stipulated time frame. So, there is only one way to cover all these things, is to practice a lot. So, requesting all of you to practice, and then in our next class we will take further things regarding circle. Okay, thanks a lot.